Okay. I see you get some responses. That's great. So let's start with today's session. I'm gonna go over chapter 1, 2, and 3. So let's begin with chapter 1. Okay. And here are the chapter 1 topics. First one is performance, execution time, cycles per instruction, clock rate and clock time period, computer organization, 8 great ideas of computer input output, processor, data path, and control path, memory, RAM, and ROM, performance, and power wall. I think few of this we're only gonna focus on the form calculation parts in this review. So I guess the other parts are covered in your class or they are either in your Xi books. So the formulas for chapter 1 are gonna be this. Performance equals 1 by execution time. It's the inverse of execution time, and execution times formula is gonna be CPU clock cycles times clock period, and this can also be written as clock frequency by CPI into number of instructions. And execution time is CPU clock cycles by clock frequency, and clock frequency is CPU clock cycles by execution time. It's derived from the same formula. And since execution time and performance are inverse, their formulas are also going to be inverse when you're comparing them and trying to find out the fourth value when you have all three values. And CPI can be calculated using this formula here. So the questions from chapter 1 are going to be pretty straightforward. I guess you guys have an assignment where you have to solve for performance and something using this formula. I think that assignment would be very helpful. And pretty much this is it for chapter 1 when it comes to the calculations part. And maybe you guys will see it in the multiple choice questions for the other topics. Now, moving on to chapter 2. These are the topics I'm going to cover in this review for chapter 2. So, for the first one, we are looking at MIPS instructions. In that, if you look at the arithmetic section, we have add, sub, MULT, DIV, MFLO, and MFHI. I'm pretty sure you guys know these basic concepts. For add, it's a R type instruction, and the way you write it is add T1, T2, T3. T1 will be your destination register, meaning it'll store the value of the sum of T2 and T3 in T1. It doesn't really matter how you write T2 and T3. Like in any order, T3, T2, it's still gonna do the same thing unless it's a negative number. So, and that's about add. And for subtract, SUB T1, T2, T3, again T1 is gonna be your destination register and T2, T3 will have the values. That's about subtraction. Um, there's a question, will you be sharing the slides afterwards? Yes, I will be sharing it with your professor, and I'm not sure if your professor is gonna use those slides. I think Professor Osman and Professor Swati will be publishing these to you. I'm not sure about that. Yeah. Yeah, multiply MULT. When you multiply the values in T2 and T3, it's gonna store in two different registers, S2 and S1, because T2 has 32 bits and T3 has 32 bits. So when you multiply this, you are gonna get 64 bits. So the least significant lower are stored in MFLO and highest significant bits are stored in MFHI. Moving on to divide, div, it's going to divide T2 by T3, div T2 T3, and the remainder is stored in T1, which is MFLO, and quotient is stored in S1, which is here MFHR. It's pretty much that's it. And logical bitwise, when you want to perform OR, like you did in CSE 120 or triple 120, you're just gonna use OR S1 S2. These will be your values, and it's gonna store in your destination register S1 the computed value. Same goes for and NOR. Yes, and NOR. And then SLL, shift left logical, it's gonna shift by 1 bit. Not 1 bit exactly. If you want to shift by 3 bits, you can just put 3 here. Or if you want 1, you can just put 1. It's gonna shift T0 by 3 bits and save that in T1. That's how it works. And same goes for shift right logical. If you want to shift right, make sure you guys remember the directions of this. These might be a little bit confusing. Here, what's happening is x equals y shift right by 2 bits. You're shifting T0 by 2 bits and storing it in T1. And the function is SRL. Moving on to immediate values. Using the immediate values, like let's say you want to add the number 2, you don't want to save that in a register. So what you can do is you can use add I or and I if you want to perform and immediate, and add I is for add immediate. You will be just adding the value 2 to T0 and store the entire thing in T1. And same goes for ORI, SLTI, and LUI. No, SLTI. And LUI is it's gonna load the upper immediate value from this hex address and store it in T0. That's what LUI is. And SLTI and ORI. SLTI is set less than immediate. Let's say S1 is holding some value. You don't know what that value exactly is, and you want to compare it with number 5. If S1 is less than 5, then T0 is equals 1. If S1, wait, yeah. So let's say S1 is 8, SLTI T0 $1 and 5. This is your instruction. Your T0 is gonna be 0 because S1 is greater than 5. If it is less than 5, then T0 will be 1. 1 and 0 act as true and false kind of values, so that indicates if it's higher or lower. Now data transfer, load word. When you're using load word, if you want to use T1 is at a particular memory, and if you want to know what T2 is or something like the next 4 bits from T1 are, you're going to use load word, store it somewhere. You need to get the value and put it somewhere. That is going to be your S0 or any temporary register. You can use anything. And you're going to use number 4 and put $T1 in the brackets. If you want to store something somewhere, you're going to use store word SW. Your S0 has some value in it. You want to store 16 bits after T1. So you're going to put 16 here and put T1 in the brackets. The people get confused between these two instructions. Load word meaning you're going to load something from here to here. Store word is you're going to send something from here to here. Moving on, load byte, it's gonna load 1 byte. SB is gonna store 1 byte. So it's same thing like LW and SW, but the only thing is instead of 4 bits, it's gonna do byte by byte. Load half word, it's gonna be half. They are all the same. It's just that how many amount of bytes you wanna go at a time. B and E, branch not equal. So let's say if T1 and you wanna do a if condition. In if condition, you wanna write in MIPS. You wanna check if the condition is happening. So here the condition is if x not equals y. How are you gonna compare it? You're gonna use B and E. If T1 is like, let's assume T1 is x and T2 is y. If T1 is not equal to T2, then it's gonna go somewhere. Meaning it's gonna do something if the condition passes an if statement. Same goes here. Label is like, I'm assuming you all know what label is. It's gonna take you to the particular set of instructions. BEQ. In the same way, it's gonna check if it's equal. So if T1 is equals to T2, then I go somewhere and perform some set of instructions. Um, SLT, it's the same thing we saw before SLTI, but this time it's with another register. Let's say T0 will be 1 if T1 is less than T2. If it's not, if it's false, it's gonna be 0. T0 will be set to 0. And these kind of SLT instructions will be useful probably when you're using BQ and BNE or some conditional statements, probably in loops or if conditions. And moving on to jump instructions, you have three in them, J type instructions. So J, JAL, and JR. J is jump. It's gonna take you, if you put J label, it's gonna jump to label and perform those set of instructions and move on. And JRRS is jump register. It's gonna take you, the JRRS is probably used in procedure calls. Once when you call the function using JAL, you're gonna jump to the function, perform some instructions, and when you use JARA, you take the return value and jump back to the next instruction of the function call. That sums up jump. And if you guys have any doubts, please note it down. We're gonna, after I complete the review session, I'm gonna have a 30 minutes discussion time. So I'll be answering your questions if you have any over that time. Okay. Moving on to pseudo instructions. Pseudo instructions are combination of two instructions. Let's say, let's look at the first one, BGT, branch if greater than. So BGT is constructed using two instructions SLT and BNE. If T0 is greater than T1, it goes somewhere. So the only original instructions will be BNE and BEQ. Everything else is pseudo instructions. BLT is branch less than. If if T0 is less than T1, it goes somewhere. It goes to the label. BGE is branch greater than or equal. It's a combination of SLT and BEQ. You're gonna get the same result when you use these two instructions or just use this one instruction. So if T0 is greater than T1, it's going to go to some label. Branch less than or equal. Same thing. If you use, it's a combination of SLT and BEQ. Yeah, SLT and BEQ. If T2 is less than or equal to T1, it's going to jump to a label. Load immediate. If you want to, um, yeah, loads an immediate value into a register. So you have an immediate value. The way you want to use it is LI. You want the register that you want to store to an immediate value. 5, let's say. I want to load number 10 to T1. So how I write it is LI $T1, comma 10. That's it. And move. It's gonna move the value from one temporary register, any register to other register. So it's gonna move. Yeah, it's equivalent to $T00 T1. So it's probably moving T1, the value in T1 to T0. Here, move, destination register, and source register. That's how you write it. And how you know these are the destination registers or these are the source registers? When you look at your MIP screenshot, it's gonna have its instruction way to write it right next to it. And then moving on to loops. You have four main components in loops: initialization, your condition, meaning you'll be using BGE, BLT, some conditional branch instructions, and update, and then you go back to loop. Update meaning you will look at it now. So let's look at a while loop. In a general in a general code, let's say we have int I equals 0 initialization. We are looping variable, and while I less than 5, you do something, and then you update I by using I plus plus and go back to the loop. So until I is less than 5, this loop is going to run. If I is equals to 5 or I is greater than 5, you will break the loop and move on to the next instruction or end your code. So initialization, like I said, we have four main components: initialization, condition, update, and loop. Initialization. So int I equals 0. We need to make sure we have everything that we need to start the loop. You don't have I, so you initialize I, and you want to compare it with 5. So you're gonna have 5 in a register, or you need to have a 5 in a register. So that's initialization part. You have everything that you need. Let's move on to condition. Let's check BGE, branch greater than or equal. You're gonna exit the loop. If I is greater than 5 or equal to 5, you're going to exit the loop. If not, you're going to move on to the next line of MIPS instruction. That is where the task is performed. And after the task is performed, you need to update. Update meaning I plus plus. So you increment it by 1. And after that, you use the jump instruction J condition. So it's gonna go back to the top of the loop. It keeps on checking the condition and updating itself and performing and exit when it's done. That's about while loop. For loop, let's look at this one. For int I equals 5, I greater than or equal to 0, I minus minus, which means we are going to decrement this time. That's our update. Initialization. You need I and you need 5. So int I Okay, we are initializing it with 5, so I don't think we need another variable here. So you're going to initialize I equals 5. Initialization is done, and then loop. We are having a condition check, branch less than branch less than, the opposite of the condition here. Exit if I is less than 0. We perform the task, and after the task line, you update it. Updating here is decrementing it by 1 according to the loop that was given to us. So I either use add I or I can even use sub. Anything works. And then you jump back to loop. Using these labels will make your code look more organized and more easier for you to understand your functions. And once the condition is hit, you're gonna exit the loop or exit the entire code. And procedure instructions. These are like your function. These are your function calls. Let's say this is your main instruction, main entity. You're calling some function fn. When you call this function fn, it's gonna yes. Look at this C code. Okay, the same thing we're gonna write it in MIPS here. Yeah, so we have function 1, 2. We are calling it with arguments 1 and 2. Here's your function 1, f1, ab, some task, and then f function 2, function 3. In all of this code, one thing that's happening is nothing is being called inside a function. Every function is being called once, that too separately. No function is being called in another function. That's what we call single procedure calls. And we have caller plus callee functions, which are not single procedure calls, which means there will be a function calling another function inside it. Let's look at this one. Int t equals fn 2, arguments 1 and 2. So we're going to jump to fn. Fn function has int a, int b as its arguments, which we do have. And then we're going to perform some task. After the task, we are calling function 2 inside function. So we go back to function 2, perform some task, and after the task is done, you return the return value back to here. And after the function 2 is called and returned everything, we return the function 1's value back to this line. So when you have caller plus callee functions, you have to use stack pointer so that you don't overwrite the values. And recursion, I'm going to share this slide with your professor, like I said, so you can just take a look at this. It's pretty much the same as procedure calls, like a caller callee function. So let's look at the main part of chapter 2, MIPS to machine code and vice versa. In this session, I'm only going to show you how to convert it from MIPS to machine code and not to machine from MIPS, but I'm pretty sure your professors have it on your lecture slides. So let's go through this one. We have 5 set of instructions, assuming L6 is going to be an exit. The first line is add $T0, $T1, and $T2. For this, we need a MIP sheet. I'm assuming you guys can view this. Okay, never mind. Our first instruction is add. So you will be given a table like this in your exam for you to fill out. Under instructions, you write all your instructions that were given to you in the question. We have add, load word, add I, BEQ, and J. Likewise, we did that. And your L1 starter address is going to be 4040 hex. That's the address of L1, which means that L2 is 4044, L3 is 4048, and so on. So let's look at the table now. You're gonna have opcode RS, source register, target register, destination register, shift amount, op function, and immediate. So before we move on to that, let's look at this over here. So for R type instructions, there are 3 type of instructions: R type, I type, and J type. For R type instructions over 32 bits, the first 31 to 26 6 bits are going to be the opcode. The next 6 bits is going to be source register. The next 6 is target. Next 6 is destination. And the next 6 is shift amount. And after that, the remaining are function. But for I, it's going to be same until target register, but then you don't have a destination register for immediate I type instructions. It's just the immediate value. So the last 16 bits is just going to be you filling out the immediate value. And for J type, you're only going to have first 6 bits as your opcode, and the rest is the address of the function. So that's how it is. So the first instruction we have is add. So let's search for add over here. You have add. It's a R format instruction. Now we know. And then opcode is 0. Function is 20. Now let's go back. Opcode is 0. So you fill out all 6 bits as 0. And okay. Now we have uh what numbers do we have? T0, T1, and T2. You're gonna fill out T0's number T1 and T2's number in RSRT and RD correspondingly. Let's look at this. T0 is 8 and T1 is going to be 9 and T2 is going to be 10. In 6 bits, we are going to represent that in binary. Yeah, binary. So how do we know which one is destination, source, or target? Again, we go back to this instruction and we look at this. So RD is going to be your T0, that's your destination, and next one is RS, and next one is RT. So if we go back to this slide, the first one is destination, this one is source, and this one is target. Exactly that way, we're going to write the number in binary for RS, RT, and RD. And then we do not have any shift amount, so we're just going to leave it as 0. And then your function, it says that it's 20 hex, so you write that in binary here. And then we have no immediate value for R type instructions, so that's clear now. Moving to load word instructions, let's go back to MIPS again. Where's load word? We have load word here. It's an I-type instructions. First one is target, and then we have source plus immediate value. So for I-type, opcode, source, target, immediate value. Where is it? Target, yeah, okay. So for load word, this is our opcode, which is 23 hex. If you only have one value on your MIPS, that means that it doesn't have any function value, so you can leave it 0 as 0. So yes, here's your opcode. RS, RT, you don't have any RD, so you leave it blank this time. You don't have to fill it out because that's not even in your section. And then immediate is, how much are we loading? 16. So we have 16 here in binary. You do the same thing for ADI and BEQ, they are pretty similar. Now let's look at J. For jump, the opcode is 2, and you don't have any of these because only first 6 are opcode and the rest is the like the value of the address, which means for L5 you're gonna have 4040 something, you're gonna do 404 something or 5, maybe C, I'm thinking. So that's what you're gonna fill in the rest of the bits. All 26 is just gonna be your address, so utilize them. That's how you do MIPS to machine code. And now chapter 3. This, I think, this is where most of the students get confused. Let's just give me one moment. There's a question. There are two questions. Will you be recording this session? Yes, this session is being recorded, but the question session, I'm not gonna record it, but I can if you want to, but I'm not sure if your professor would want to upload that. And another question, do we have to fill this table as the part of exam? Did you mean this table? If it is, okay, that is. Yes, you will have to fill this out. I'm pretty sure you'll have a place to like a working place to work on it, the blank page or something, but then you have to fill out some table like this. I'm not sure if the format is asked, like if it's a R format or I format, but yeah, there will be a table. And remember, since it's a I type function, it doesn't have destination register or shift amount or function. If it doesn't have in its structure, like in here, just leave it blank, don't fill it with zeros. Okay, that's it. That's with our questions for now. Moving on to chapter 3, all about floating, yeah, binary, nothing to do with MIPS. So This is the part where most of the students get confused. Like I was saying, let's look at this example. They're gonna give you a number, and ask you to represent it in 8 bits or 6 bits or 10 bits. Up to them. Let's look at an unsigned number, 39. Not unsigned number, it's just a number. Let's look at a positive number, 39. Unsigned, when it's a decimal number, right? So you're gonna have to do that division thing to convert it to binary. When you do that, you get this. 0 B is nothing but it just says that it's binary, so don't worry about B. 0 0 0 1 0 0 1 1 1. This is 39. When you have it signed, it's still gonna be the same because its sign is positive. So you don't have to flip the bit. You yeah. Okay. Never mind. I was distracted by the participants joining, but yeah. You don't, if it says unsigned or signed, it'll still be the same because it doesn't have a negative sign on it. So it'll be exactly the same. And once complement, you're gonna not flip everything because it's a positive number. Why did Yeah. And two's complement is also gonna be the same as one's complement. And for minus 39 in 8 bits, this is your signed number. The only change thing is the first bit after B. So 101 0 0 1 1 1. And it's not gonna have an unsigned value because it is negative. And for one's complement, you flip every bit but the first bit for the first bit because it's representing the sign. And same goes for two's complement. So yeah, that same goes for two's complement. You don't flip the first one. I guess that is clear now. Binary addition and subtraction. I'm pretty sure you guys have seen this table when you're doing your Triple E 120 or CSE 120. Same thing works here. If the numbers don't add up how they're supposed to, then it's an arithmetic overflow. Save this table. If you guys have a cheat sheet allowed in your exam, just put it on your cheat sheet. You don't have to remember much. If you just follow these conditions and something comes out of this table, like your result is something that's not matching any four of these conditions, then it's an overflow. So yes, that's how this is. And the people who are joining just now, if you guys have any questions, please note it down. I'll be answering them after the review. Okay, that is just about arithmetic. Now moving on to binary multiplication. I'm pretty sure that you're gonna have either multiplication or division in your question paper, either of these or both of these in the worst case. Not a worst case, but yeah. I think only one of them, but let's go over both of them now. First, binary multiplication. To sum up everything that you have on your lecture slides about multiplication, I have this picture over here, steps for multiplication. So every time if your um if your multiplier's last bit is 0, product equals product plus multiplicand, and then after you do that, you shift multiplier by 1 and multiplicand by 1. If not, if the multiplier's last bit is not 1, what you do is you don't add anything, you just keep shifting. Okay. That's the simple logic. Maybe even have this on your cheat sheet. You don't have to get confused. It's like pretty straightforward. Let's look at this example now. Multiply 0 1 1 0 and 0 1 0 0 1 1. Let's take 0 0 1 1, which is 3 as multiplier, and 0 1 1 0 as multiplicand. Let's go through this little cheat sheet we have here. Is multiplier's last bit 0? Sorry, last bit 1. It is. So since it is 1, We are gonna add product, which is 0. Our starter value, the product is gonna be 0. 0 plus multiplicand, which is 0, 1, 1, 0. And we keep moving. And after that, we shift it to the right and 1 to the left. Yeah. After that, we're gonna do the same thing over and over again until every bit in multiplier is just done. So now we have 0, 0, 1. It's the same again. So the last bit is 1. You're gonna add 0, 1, 1, 0 to 0, 1, 1, 0, 0. You're gonna get 0, 1, 0, 0, 1, 0. Store it in the product. And now we have all zeros, which means we are not gonna do any multiplication. So that can be your final answer. But just in case if your professor asks for it, just keep continuing this loop we have here and you'll get your product value. That's your answer over there. It's pretty much that simple. All you have to do is keep checking the conditions over and over again. That's it with multiplication. And let's go to, okay, the heading is wrong. I'll update the slides. Oh, okay. Just give me one moment. I think I have the wrong slides too. Okay. We'll go over binary division at last. I have the wrong slides here. I'm gonna change it. But I'm gonna talk about, yeah, I'm just gonna talk about it later. Now let's moving on to floating point. Um, there are two types in it: single precision floating point, double precision floating point. In single precision, you have 32 bits, and in double, you have 64. In single precision, the first bit is going to be your sign bit, which means 0, positive, 1, negative. That's going to represent your sign. The next 8 bits will be your exponent, and the rest remaining 23 bits will be your mantissa. In double precision, first bit is sign, next 11 bits are going to be exponent, and the rest 52 bits will be your mantissa. This is the difference between single and double precision. They're going to mention it to you in the question, so don't worry about how to really identify it. I'm thinking they're gonna, yeah, they should let you guys know. So now, how to convert some decimal number to binary? Let's look at that. So you have, let's say you have a decimal number minus 61.75. You're gonna write that um, in single precision and also in double precision. So you're gonna normalize that thing, that number, and after that you will get a exponent here. What you want to do is after you convert that, you will have to only have one digit after the decimal, like before the decimal point. So how many times ever you jump, it's gonna multiply by 2 times 5. Like I jumped 5 bits here, so it's 2 times 5. So our biased exponent is gonna be 127 plus whatever number we have about 2. We have 5. So it's 127 plus 5. It's 132. And yes, after that, we write that thing in binary, meaning in this entire thing. So this first bit here, -1, will be your sign bit. One bit is going to be sign. We have negative, so 1. And after that, this binary, we're going to put it next. That's your exponent, 132. And the remaining digits, all after the decimal, it's going to go into your mantissa. You don't really have to write out your entire mantissa every time, because sometimes it's going to be 23 bits, which maybe you can, but for double precision, it's 52 bits. I don't think your professor expects you to do that. And the only difference between like converting decimal from single to the single or double is your biased exponent is gonna change. Your biased exponent for double is gonna be 1023. We do the same thing again, 1023 plus 5, 1028. And 1028 in binary is this number. So your sign is negative, so sign bit 1. Your binary, your exponent is um next. You put that in next 11 bits. Let's say you only have like you only got like 10 bits. You don't know what to do with the 11th bit, just add a 0 in front. And then after that, your mantissa, the remaining decimal part. And after you write everything, it's on like result is gonna be here in hex, which means you will have to divide by 4 4 4 4 thing, like from binary to hex. You know how to do that, I'm assuming that. And yeah, that's how you're gonna write your result. And after, you might have a question, what's after this 1110 111? It's gonna be all zeros after that. So don't worry about that. That's why your professor doesn't expect you to write everything. Okay, moving on to floating point addition. You're gonna have some decimals given to you, 2.450.11. Just like how we did it here, you're gonna do it again the same way. And when you do that, you might get most of the times you'll have different powers, 2 to the power 1 and 2 power minus 4. For operand 1 we have this number, and for operand, what we try to do when we have two different powers is we try to match the power, like the greatest power here. Over 1 and negative 4, the greatest one is going to be greater one is going to be 1. So what you try to do is you try to convert this second operand to match the first operand's power. So that is going to be you shifting 4 times to the front, which will give you additional zeros. So now the power is 2 power 1. When you will always have to make sure that your powers are same. And after that, you can leave aside the 2 power 1 part aside. Just add the numbers 1.011. You don't have anything, so you assume you have zeros after that. And the second operand, we write it here. So 1, 1. We do the binary addition here. So 1 plus 0, 1, 0, 0, 0, something like that. Let's say you have 1 plus 1. So 1 and 1, 1 below 1. You're gonna write 0 and 1 over the next digit. That's how this floating addition is gonna work. And then after that, you will get some result. Here we got 1.00 and then 1111. It's a positive number since none of our things are negative, none of our operands are negative. Into 2 power 1, and 1 is in the range, like the range is for checking the power of your 2, and 1 is in the range of minus 126 and plus 127, so no overflow. And sign is 0, so the first bit is 0. Biased exponent is 1 plus 127. You're going to perform everything that we did here over here, and then just write it out in the hex form at last. And if you're again wondering how do I know if it's a single precision or double precision when I'm converting the result we got into our this normalized form and stuff, they're going to mention that to you in the question. So they're going to ask you to perform a double precision addition or single precision subtraction. And then how to do the multiplication? It's pretty much the same things. You add the exponents, multiply significance, normalize the product, and truncating means doing this mantissa sign thing. You just need to arrange it in the correct form. So now we will just go, just give me one moment. I'm gonna stop sharing my screen and try to find the question for division part. Okay. Let me share my screen again. So, ignore the name. Let's talk about division algorithm. Just like how we had some simplified, straightforward understanding of multiplication, like steps for multiplication, we have the same for division here. Again, put this on your cheat sheet. It's gonna be really helpful. So the way this works here is you have reminder. Reminder equals reminder minus dividend or divisor. Okay. You know what? Let's move to this one. You're gonna have divide this number by some number. What happened? Okay. Divide this 0, 0, 0, 1, 1, 1 by 0, 0, 1, 0. Your quotient is gonna be 0 from the beginning. Your divisor is your 0, 0, 1, 0. We will just have 8 bits just because we have the reminder in 8 bits, which is your dividend. So 0, 0, 0, and you have everything in 8 bits, quotient in 4 bits. That's your initial step, iteration number 0. Now let's move on to iteration number 1. You're gonna shift left. So what you're going to do every time is reminder minus divisor equals your reminder again. So the first time we performed that, we got 0, 0. Okay, I'm gonna. This is a bit confusing. Let me try to simple it down. Okay, so let's talk the algorithm again. I'm sorry for the confusion. Let's start fresh. We do this step every time. In every iteration, one thing we do is reminder, we update the reminder with reminder minus dividend value. So after doing that, we are going to have a new reminder. If reminder's entire value is negative, which means less than 0, we will have reminder equals reminder plus dividend, and we are going to shift quotient by left, and then um yeah, shift quotient by left by 1 bit. If not, we are going to do nothing with reminder, which means if reminder is positive, we are not going to add anything or skip, we'll just skip this step, and we're going to shift it left by 1. If it's negative, we shift it left by 0. That's it. That's the, sorry. Yeah, that's the algorithm. Now let's go back here. We are doing reminder equals. Okay, I'm not sure if you can see my. Can you guys see my mouse pointer? Okay, great. You guys can see my mouse pointer. So let's go to first iteration. What we perform? Reminder minus dividend. Sorry, divisor. We perform that. We got some value here. Equivalent 0, 0, 0, 0. Is it less than 0? No, it's positive. We don't have any negative number here. If it was negative, we would have a number 1 in the beginning. So it's positive. We do nothing. We just shift divisor right by 1 bit, which is 0, and quotient again left. We just keep shifting them, and we're going to do the same thing until this step. Um, okay, in step 2. Okay, when we just give me one moment. We have this value in. Actually, I think we should skip this division example because I don't think I have the right example exactly right now for you for like to show you guys. But yeah, this I'm really hoping this algorithm here is gonna help you. Just have it on your cheat sheet. Do the same thing like we did for multiplication. I'm just gonna give up on this division example because I don't wanna give you guys wrong information and make you guys lose your points. So we don't have an example, so we're gonna skip it for now. Please make sure you ask your professor if you have any questions about your binary division or your TS. I'm pretty sure they're gonna help you. And now we end the review session. Okay, since we're done with review session, do you guys have any questions?